So you may or may not have seen the full list. So if you want to do the seismic assessment of existing buildings, you need to familiarize yourself with the full set. And it goes from A to B to C. And there are 10 parts of C, which is really looking at the things you need in the DSA. Tonight, we're going to focus on part B, which is about the initial seismic assessment, and it's on the assumption that you're already familiar with the section A on the objectives and principles, which gives a nice overview and introduction to the seismic assessment of buildings in New Zealand. For those of you Redco, these documents are available via our common drive, and for everybody else, you can get them and download them from the eqassess.org.nz website, and they're freely available. And quite substantial documents, particularly the later ones, because they go into a great deal of detail on a material by material base for seismic assessment. So, oh, by the way, most of the pictures in this presentation and in the previous presentation are my own photographs taken when I was wandering around Christchurch in 2019 and 2020, having a look at the damage caused by the 2011 earthquakes. So, as I've said before, many seismic assessments start with an IEP. So even if you're going to do a detailed seismic assessment, then you always start with an IEP and an ISA and write them up. So what this does, it's a quick and dirty way of assigning a NBS. What's a percent NBS? Well, it's a new building standard rating, and it gives a grade associated with that rating. What it does, it allows building owners and building managers to review their building and establish the risk of that building from a seismic point of view. What we're doing is we're assessing the capability of the building to resist an earthquake and compare it to how it would perform under modern loading. So the current design standard, that's NZS 1170 Part 5. It's an indication how well the building protects life when compared with a similar building that would be built on the same site that just complies with the minimum standard required by the Building Code of New Zealand. Now, bear in mind, if your building is designed and built properly, most newly constructed buildings should have a percent NBS building well above 100. And certainly in our case, most of our low-rise buildings, seismic issues are not the driving criteria for their design. However, it doesn't predict how well the building will perform in a particular earthquake. So an earthquake is complicated, and the effects of that earthquake or any earthquake on a particular building depend on many factors. So how do we do it? How do we do our initial seismic assessment? Well, it starts with a desk study. So you need to research and collect and review all the records you can for the building and look at the construction features and the heritage significance. The best source initially will be the council file, unless your owner has the original documents. Quite often you'll be dealing with old buildings, and quite often those records will have been lost, and usually the only record is what we have scanned in the council file. Hopefully the council file will have drawings of the building, which helps enormously. Sometimes you don't, so you have to do your own sketches. The next part is the on-site survey. So conduct an exterior and interior visual inspection. And I say visual, this is usually not an intrusive inspection. You tend not to take things apart or take samples for initial seismic assessment. Then you complete the IEP spreadsheet, and then you can prepare the full ISA report. Now in your handout, the IEP spreadsheet will link from this link here, if you click on that. And there's a link between the IEP spreadsheet and the ISA report. So let me just flick it across. So this is the IEP spreadsheet. Now, before we dive into that spreadsheet, let me tell you a bit more about the background. It comes from the Initial Seismic Assessment document from the NZSEE. So this is part B. And before you do an initial seismic assessment, you really should be reading this document in full and know your way around it, because this is where the template comes from, and this is explaining what the parameters really mean, how to fill in the boxes. Let's go through this document in brief to begin with, and it explains the process step by step. And there's a little flowchart that tells you the process, some definitions and acronyms that will come across, and the symbols used in this document. There's an interesting concept called potential critical structural weaknesses, the CSWs, and the potential severe structural weaknesses. Now, we'll talk about those a little later and what's the difference. But during your inspection and assessment of the building, you need to pick out the critical structural weaknesses as well. Bit about the background, and this will help you understand the process you're doing, and it will help you write the report, because as part of this, here's how to do the report and what to put into the ISA report. And we then, it also within this document tells you the limitations you need to state. So there's a lot of limitations and restrictions on the use of an ISA, and that's what you really need to explain to the client. It's not a magic bullet. It will help you in some ways, but may not in others. So we come to the appendix, and so you've got Appendix BA, and this outlines the initial evaluation procedure, or IEP. And sometimes clients think that's all they need. They just need the spreadsheet, which gives them the score. Now, if you're a good structural engineer, you won't do that on its own. You will do it with an initial seismic assessment. So you need to explain to the client in your report what this percent NBS actually means. So let's blow that up a little bit. And it goes through it step by step. So collect the information, as we've said. Plans, specifications, if you're lucky, photographs. Google is very handy on this, Google Maps and also Google Earth, so you can wind the clock back and possibly see historic photos, which can give you an indication of how old the building is if that's not known. And then the step is to determine the baseline percentage NBS. So it's a simple calculation, just A times B times C times D, as shown in the IEP spreadsheet. And that's your starting point, and that often is quite low. Then you want to know what the ratio is. It's called a performance achievement ratio, or PAR. So you multiply what you've got from your first edition to get your PAR, and then multiply it by the provisional NBS to get your percentage NBS. Then, depending on the value, you need to know what to do. So if it is less than 34%, your building is potentially earthquake prone. If it's between 34 and 67%, your building is possibly earthquake risk. And if it's above 67%, then we tend to think of it as a low risk item. If it's below 67%, we would normally recommend a detailed seismic assessment before confirming the building as earthquake risk. So you shouldn't really use an ISA as the basis of determining whether the building is actually an earthquake prone building. And as you recall from the last session, it's not up to you to determine or declare the building to be earthquake prone. That is the job of the territorial authority, and they will take their advice based on your report. And if your report hints at it's less than 34%, then there's a good chance that the council will say, yes, it's an earthquake-prone building, write to the owner and ask the owner what are they planning to do about it. So there's also a grade A, B, C, D, E that goes with your percentage NBS. And as part of the process, you will have identified any severe structural weaknesses and whether the building is a risk to its occupants as well. So that's the first part of Appendix D. Here is the template. This is where the spreadsheet comes from. And we'll go through it bit by bit in a moment. So just skate through that. And they do it once in one direction and again in the other direction. So longitudinal and transverse, on the assumption that your building is more or less rectangular and has frames or walls, columns and beams, which are at 90 degrees to each other. This explains where some of the factors come from in the spreadsheet. So if you run through the spreadsheet and punch in some numbers, it'll just pop out with a number and it's not obvious where it comes from. Well, this will tell you where it comes from as well. And there's an R factor as well to consider, depending what you're doing. Ductility factors. Now, these are a bone of contention as what you do with your ductility. Yeah, 6 is pushing it post 1976, but generally for ISAs, I wouldn't take any more than 2 for your ductility as well. So this is where some of the parameters come from, your performance criteria come from, and some historic maps from how we used to do seismic design in New Zealand and the zones. So on and on it goes through the various pages, but what I wanted to get to is the end of it. And at the end of it, you do the assessment of whether you've got severe structural weaknesses, which might pop up and tell you that your building may not be occupied or shouldn't be occupied or otherwise in there. We'll come back to that. And it's signed off by a chartered professional engineer as well. So the second part of Appendix B gives you guidance and commentary. So you've already been through the process step by step. Now this part of the document takes you again step by step and explains a little bit more as well. So some definitions are given here as well. So we'll come back to that a bit later, but right at the end, there is another issue about unreinforced masonry buildings. So there's a separate methodology for that. And again, I'll show you an example of that because you get an attribute scoring system. Now, chances are if your building is made of unreinforced masonry, it's probably earthquake prone. It's quite hard to justify when the main structural elements are unreinforced masonry to be anything other than earthquake prone. But you do this little assessment and tot it up. So here's one I prepared earlier for another building. Let's see if we can blow that up a bit. And you go through it item by item, giving it a score from 0 to 3. So is it continuous? Yes, no, or none. And sadly, the higher the score, the worse it is in there. And you look at things like horizontal regularity and vertical regularity and planned regularity. So if you've got a nice square building where all the walls are in line and the plan is continuous all the way up the building, then you're looking at excellent. If not, if you've got something that's what we might call higgledy-piggledy, irregular on plan and irregular on elevations, with steps in the elevation and setbacks on your stories, then you might be looking at an attribute ranking of 3. Similarly, you need to take into account the condition of the structure. So there's a fair amount of cracking in your brickwork or your block work. then you're looking at a poor performance as well. There is explanation in the book about when it's the proportions you need to be good performance or poor performance as well. And the separation is really about the pounding issue. And you add all your numbers and tot up to a score. In this case, the score was 17. What does that mean? So you multiply the score, and if the score is between 15, in this case, between 15 and 25, your percentage NBS turns out to be 31, because we've already taken our RX as a 1, and we know what our Z is in Auckland as 0.13. That turns out to be 31. So that kind of tells me that this building is probably earthquake prone, which was a pity because it was a very nice building with lovely brickwork in it, but unfortunately unreinforced. And as you may have noticed, there isn't a code of practice for unreinforced masonry in New Zealand because you're no longer allowed to use it. But many, many buildings in New Zealand are made of unreinforced brickwork. Historically, the British came over and built the towns just as they were in England. And there's no coincidence that Christchurch looks an awful lot like Cambridge in there. So that's going through the document, the Initial Seismic Assessment document from the NZSEE. Let's jump back to that spreadsheet. Here we are. So we've had a glimpse. So here's one I prepared earlier, and this is for a building in Palmerston North. Palmerston North been in a fairly high seismic zone as well, not far away from the big fault. So you start with some photos and some sketches or extracts from drawings if you can. It gives you a little space to tell you about the building, but I tend to put more information in the actual report itself. What have you done? Have you done an exterior or interior evaluation as well? Have you got drawings? Have you got specifications? Have you got a geotechnical report? Quite often your initial seismic assessment won't have a geotechnical report. You won't have done a site investigation or any geotechnical records. What you can do if you're suspicious about the ground is go on to the GNS portal and download site records for boreholes and trial holes in the vicinity. So sometimes I do that to give you an indication of what the ground is doing. Similarly, there are historic records you can find on Google about potential earthquakes or ground movement in the area. So now we get into the meat of it, the initial valuation procedure, step 2, which you get your baseline NBS from this. And this is one of the driving factors, probably the biggest driving factor is when was it designed? And that's not necessarily when it was built, because your design code can be in use long after it has been superseded. And so even though your building was built in 2010, you might find that it was designed to a 2004 code. So you need to tick this box here for the 2004. And it makes quite a big difference because the loading you would apply now is significantly higher than it was in 2004. Now, some of these will become available depending on the selection above. Also, this spreadsheet has pop-ups. So if you want to know more about seismic zones, it pops up with the maps taken straight from the document as well. Soil types. So this is geared at what we've got above as well. So we know it's either A, B, C, D, or E. And depending on when you're doing, these may come up as well. So sometimes those will be blank. Now, we know there's going to be a minimum period of 0.4, but you can calculate an approximate period which could be longer than 0.4 if necessary. Now, for concrete resisting moment frames and moment resisting steel frames, it's simply a case of putting in here and it will calculate your period based on that. For concrete shear walls, there's an extra pop-up, and if I select that, it magically brings up this extra spreadsheet, which allows you to put in the lengths of the walls and the thickness of the walls for the levels you're talking about. And it kind of assumes you've got the same wall arrangement all the way up the building. So these are going to be the main lateral load takers, load-bearing elements of your building. So click OK to go back. So from that, it will usually pop up the values of A, B, C, and D. And so all of these figures are derived from what you've put in above. And that's your, what we call our nominal percentage NBS. As you see, it's not very big. So then we go and make some more excuses for it. And we put in our hazard factor, which is unfortunate because it's called a factor F, and yet there's another factor F further on. And the factor F is derived from the values you put in for Z in here. And if you want more information, again, just click on the pop-up by the side of the spreadsheet. There's that. And if you want to add a user-defined, you can do. If you want to know more about the I's and the RO's that are used to find your G factor, again, click on here. And this varies depending on the year of the design you're looking at as well. So it comes down to, quite often it'll resolve down to 1. And if you've got an importance factor, you need to put it in here. Again, if you can't remember what importance factors are and how they apply, then click on the button and this table pops up, and this is the table from 1170 down. Now this again is basically a free-for-all. You can put in pretty much any number you like from 1 to 6, and recommend you don't put in 6. But here's the more discussion about the levels of ductility you can use, and generally you'd be looking at less than 2, unless it's a particularly modern building, steel framed or RC framed building that has specifically been designed with ductility in mind. And it's not just designed, it's detailed with ductility in mind. And that's a relatively new thing. So take care with the ductility. The scaling factor comes from the performance factor, and then you multiply those together and get your percentage NBS. So that's your starting or your baseline percentage NBS. Then we add some more factors. So we're looking at general buildings or a generic building, and now all of these factors will tend to put them down. So you're looking at your potential critical structural weaknesses. So we're looking at plan irregularity, vertical irregularity, or whether we've got short columns. And whether it's insignificant, significant, or severe is defined in that code again. So there's a pop-up that tells you whether it's going to be severe or significant. And if it's severe, if I switch on severe, the factor drops to 0.4. So it makes a big difference. If it's insignificant, it goes back to 1 as well. Then you're looking at pounding. Pounding is one building crashing into another building. So if your buildings are close together in an earthquake, there is the potential for the two to smash into each other. And again, click on the more information button to find out what you need to know about pounding. So what are the limitations? One is how close is the building? How near is the adjacent building? But also, are the stories heights, i.e. the floor levels of a similar height? So if you've got a very tall building with big floor-to-floor height, it can have a big difference on your pounding effects as well. So you pop those in, whether significant or not significant, and factor D comes out. Now, normally if there's no reason to suspect the ground, then your factor is E. But if you suspect something like a landslide, instability, or liquefaction, then you need to downrate it again as well. If you really do suspect liquefaction, it's not really something you should be assessing. It's something that should be assessed by a geotechnical engineer as well. Now, here's the other F factor. And it allows you to go from, well, 0, which we daft, all the way up to 2.5. Now, if it's greater than 1, you are asserting in your engineering judgment that this building is better than it is by the evaluation you've just done above. If you, on the other hand, put it less than 1, then you're asserting that it's actually worse than those figures apply above. And this is really what I'd call a fiddle factor, and it's down to the engineering judgment of the structural assessor in there. So that pops out as your PAR. And as you follow it down, you then do the same thing again in the other direction, the transverse direction. You can have two different percentage NBSs, one in the longitudinal direction and one in the transverse direction. The total result is the weak. So the building is only as strong as its weakest part. There. So you're nearly at the end now. You've got your assessed baseline, you've added your PAR, you've multiplied the two, and that gives you your seismic rating. In this case, it's 25%. So is it less than 34%? Yes. So potentially earthquake prone. Obviously, it's a potentially earthquake risk as well. So the grading that it pops out, this pops out from the percentage NBS you've done. Now, this gives you an opportunity to say why you think those figures are real or unrealistic as well. So perhaps the condition of the building has led you to put in a lower rating than otherwise would come up. So if it's in poor condition, your F factor might be a 0.7, 0.8, something like that. And so the relationship between your percentage NBS and your grading is written down below there, all the way from A+ to E, running from more than 100% down to less than 20% as well. So that's the body of the IEP spreadsheet itself. You've done all that, and then it says, are there any potential severe structural weaknesses? Now, this really only applies to multi-story buildings, and it really only applies where you've got what they call heavy concrete floors and or concrete roof. So if you've got a concrete floor or a concrete roof and it's multi-story, then these would stop being grey. So if I just change that, let's say I've got a 5-story building and I've got heavy concrete floors, then these options will become available. And so they're no longer grayed out. So do you have a weak or soft story? So quite often multi-story buildings have big open spaces on the ground floor, and a floor-to-floor height on the ground floor much taller than on the other floors. This potentially could be a weak story. In the design, is there brittle functions in your column and beam to column connections? Is the slab relying on low ductility reinforcement as well, i.e. the reinforcement between your slab and the column connections as well? It may have a diaphragm, but is that diaphragm tied into your primary structure? Okay. If I go even taller, then another option pops up. So you need to look at whether stairs, particularly precast concrete stairs, can they fall off their supporting ledges? So these, as I say, are only applicable to multi-story buildings, and in particular concrete multi-story buildings as well. For many of the ones we're assessing, they're 2 or 3 stories. So what does it mean to have a severe structural weakness? Well, if you've got any of these, there's a potential for what they call a pancake failure, which is we called a progressive collapse, as if you recall from seminar number 3. So that is available, this spreadsheet, IEP spreadsheet is available for download from the EQ Assess website, and it's available from fairly other sources as well, including our own Common Drive and templates. So that's the IEP, and that gets you your percentage NBS. So then we move on to the ISA report itself. So here is our ISA report. Now within our templates, if you fire up ISA report, you will get a Word template for this. And again, this is one I prepared earlier for the same building. And it has our usual macro-derived titles, project numbers, and authors, reviewers, and signatures. All right. So again, I like to put a picture in at the first page. Have an executive summary, because it's the only thing the executive will actually read. And this tells you who employed you to do it and what you were employed to do. So in this case, it was an initial seismic assessment of this particular building. What does the building do? Well, it's a steel-framed commercial and retail building. So we give them the headline news. In this case, it tells me that the rating is 70%, 75% NBS, and you give the importance level. So the percentage NBS is always accompanied by the importance level. This sharp-eyed ones will spot this is different from the IEP spreadsheet I just went through, but that's because I was changing the IEP spreadsheet to make things worse as we went through. And include lots of appendices, in this case, photos of the building, the engineering assessment summary report, which council love, and the Department for Education demand. You include the IEP report that you've just done, and in this case, some borehole logs. If you've got any geotechnical information that you've used to assess the building, and stick it in at the end as an appendix. So I like to give a site map, a location map. There's the context. We start with an introduction. We put in the limitations. So the limitations are boilerplate text, and that boilerplate text comes from the document you've just been reading, the NZSEE guidelines as well. So all of this, the background to the IEP and its limitations, tells you all about it. All about what we're doing with an ISA. So it's a qualitative process, and it's expected to be undertaken and overseen by an experienced engineer. Okay, so this was our brief and the scope of what we did for our fee. We say we research and collect and review records, and we then do a visual inspection of the interior and the exterior, conduct the ISA using that IEP, and then we prepare the full ISA report, which is this document. So we begin at the beginning, give a description of the building. It's also useful to know the lie of the land, so the topography and the geomorphology of the land, and this can often be found from technical records, geological records of the area as well. Here is an aerial view we've got from the GNS website. And so these are where the geotechnical records have been obtained. And these are the nearest borehole records to our site. It's a little bit cheeky, but it's all we've got at the moment before we do a full site investigation. So as I've mentioned, the GNS holds the 2 borehole records and describes what the ground is. So from that basis, I've said this is likely to be a Class C shallow soils. What's the site history? What's it used for? And what's it been designed? So sometimes you'll have the original calcs and by whom. And there's, the code that was used has since been superseded, but there's a grace period, as we say. So sometimes this older code was used long after it was superseded. And that was because you get a cheaper building in there. I like to stick in some of the drawings or extracts from the drawings as well to find my way around it. So I've spent an awful lot of time going through the records and digging these drawings out. I might as well use them as well. So here are some sections through the building, flying through this. Some more details of the steelwork and details of the foundations. Now, it's unlikely you'll be able to investigate the foundations of a building that's been built, or you're unlikely to have trial pits and trial holes against the foundation. So there's a fair amount of assumptions you have to make about the foundations. If you're lucky, you'll have drawings like this for the foundations of the building. So you do a structural inspection. So that was described in a previous seminar. So go back and have a look at that video as to what we do when we're examining a building. So general comments, it's pretty good condition. Everything was covered and so on. What were the primary load-bearing elements? In this case, a steel portal frame. Got to describe what the lateral loading is resisted by. Has it been altered? Because quite often you'll come across buildings that have been altered, not always for the better. And what was it being used? Was it occupied as well? Chances are you won't be able to examine the roof. Sometimes you can from adjacent buildings as well. So item 6 is you identify the potential critical structural weaknesses and the building resilience. So in this case, we didn't find any critical structural weaknesses, neither did we find severe structural weaknesses. It's not really surprising as a relatively modern steel framed building, and it's only single story. So we then come into our assessment results. Explain the grade. So what does it mean to have a grade 75% NBS? It means you've got a low to medium risk building, for example. So it's a grade B, a low to medium risk, and so on. Worth looking at non-structural items as well. One of the favourites in housing is hot water cylinders in the attic or the loft not being properly secured. Other items are canopies, parapets, so forth, not being properly secured. If there is a building close by, do they interact? And if your building collapses, will it affect the neighbouring building? You need to think about that. Have a word about secondary items. Now, we don't go into these usually in the IEP. So we're now on the IEP plus stage, as it were. So things that can pose a risk to life safety: parapets, canopies, building services plant, quite often it's put up and not secured. Certainly doesn't often have seismically designed restraints to it. Glazing, large areas of glazing overhead or at high level can pose a threat to life and safety. If you've got heavy ceilings, particular plaster or solid plaster ceilings and plaster cornices, they can pose a risk as well. In this case, there's no issues as well. You can give them a nice conclusion with that, and usually by that stage, because we're above the 67%, that's kind of the end of the story. That's the end of the job. If it was less, you'd then go on to the recommendations. And one of the recommendations could be to do a detailed seismic assessment to get a more accurate percentage NBS. And then we're into appendices. So Appendix A is the photo section. If you're doing a survey, take lots of pictures inside and out from lots of angles. You'll sometimes capture images you'll have forgotten and won't notice at the time of doing the inspection. So here we see into the, having said we don't do an intrusive investigation, it won't hurt you to remove a ceiling tile. Ceiling tiles are usually easy to remove, particularly these lightweight commercial ceilings. And you can pop your head up into the ceiling void, and that's where you get a decent look at the existing structure. The Appendix B is the summary report. This is usually imposed upon you by the council or by the Department of Education, because what they like to do is take this, process it, and shove it straight in their database as well. A lot of this information you will have derived from the previous events, so this is just summarizing everything you've done so far as well. A little bit about the person who's signing it off and the drawings you've reviewed. If there's a report, a geotechnical report, then you reference it here. Dates of when it was inspected and so on. Any testing you did and any previous assessment reports. You might get previous assessment reports by different engineers from different dates, which give different results. So you may want to comment on that. So I shove in these. These are the assumptions I have made and sometimes why. In this case, they're all one. If they're all one, there's not a great deal more explanation to do. But if they're anything other than one, you need to explain why you've picked those figures as well. This section is for DSAs, and then it explains which parts of the 10 parts of Part C you've used as well. And the outcome, is it sufficient, this ISA, or do we need to do a DSA? Did you notice anything weak about the building? If you're going on to a DSA, you fill in this form all over again and identify the weaknesses. Not just identify the weakness, but explain the mode of failure, particularly if it's going to be a brittle rather than a ductile failure as well. And if it's an earthquake-prone building, you need to make recommendations as well. Okay, so Appendix C gives the IEP form, which is basically what you've just seen, and then Appendix D gives you your borehole logs. So once this is all converted into a PDF, it all goes together, signed off, and then that goes to the client. So that is the report for the ISA. That is the IEP for the ISA. Okay, let's go back to the show. So what are the issues? Well, what do we mean by critical structural weaknesses, CSW? So if it's insignificant, the real threat is it's unlikely to lead to loss of life or property damage. When we say property damage, we really mean next door, to damage to neighbouring properties. If it's significant, there's likely to be moderate loss of life and likely to be damage to the adjacent property. Severe is, yes, likely a severe loss of life. Now, the document doesn't actually define the difference between moderate loss of life and severe. I think that's left to you to decide as well. Now, severe structural weakness. Now, these are only applicable to if you've got more than 3 stories and you've got floors and roofs which are heavy, then you need to consider the severe structural weaknesses. And these are weaknesses that are associated with catastrophic pancake collapse. And this is what I've called disproportionate collapse in my early seminars. So, as mentioned, a weak or soft story. This is a common cause of failure in commercial buildings, in commercial multi-story buildings, that the lowest story, although it's the heaviest loaded, is often the weakest, particularly to lateral load. Have you got brittle columns and brittle column connections? And that may be revealed by the drawings. If you've got for example, reinforced concrete, you'll see where the containment steel is or isn't, and see whether the reinforcement is continuous or not, and whether the lap lengths are adequate. Is it a building with a flat slab? And if so, is that flat slab reliant on the low ductility to the slab column connections? And if you've got a diaphragm, is there an effective or not connection between your diaphragm and the other lateral load resisting elements? And if you go over 6 stories, now they only put this for the taller buildings, based on the idea that the taller the building you have, the more likely the spread of the gap between your stairs and the supporting structure is going to be large enough to dislodge the stair. So, is the stair likely to fall off? Another issue with stair, though, is sometimes the stairs are supported halfway up a masonry wall. So a seismic event will then put lateral loads out of plane on a masonry wall, which can lead to its collapse, which will lead to the collapse of the stair. If any of the above, it's a potential earthquake-prone building, and you then have to justify why it's not an earthquake-prone building. Okay, here is our risk explained again for each of our seismic grades. And as we've mentioned before, A and A plus, no problem at all. If it's E, then you've probably got a problem with your building, and it's more than 25 times riskier than a normal building. But bear in mind what we said before, that's relative to a brand new building. And remember that we've said that the chances of fatality in a modern building are 1 in a million, which is roughly the chances of a fatality from a lightning strike in New Zealand. So what are the issues? Well, as we've said before, ISAs are quick and dirty. They're over-conservative, deliberately so, because the whole point of the ISAs was to allow territorial authorities to run around the country and assess their buildings. So it needed to be quick. It is harsh on old buildings, and it's very harsh on masonry buildings as well. On the other hand, DSAs are long and expensive. As I say, it should be priced as a total redesign, but they're usually not, and they're usually underpriced. People think, it's just like a DSA, it's just like an ISA times 2, maybe times 3. No, keep timesing. Think of it as a new design. Okay, seismic strengthening. Treat it as refurbishment, and the problem with refurbishment and a major refurbishment at that is you don't know the full extent of the refurbishment until the building is underway, and you don't know what you might find until you start opening up the building. So I pointed out that the document section B of the NZSEE guidelines points out that the IEP is a largely qualitative process, and it requires considerable knowledge of the earthquake behavior of buildings and judgment as to the key attributes of the effects on building performance. So it's not a tool that can be applied by inexperienced personnel without adequate supervision. Unfortunately, it has been, and quite often IEPs were done by graduate engineers who didn't really understand the seismic behavior of buildings. IEPs, I would say, must be carried out and must be reviewed by a CPEng. If it's carried out by a junior engineer, they need to be closely supervised as well. So they need to have sufficient experience in the valuation of these earthquake effects, and preferably receive training in the process. Okay, so that's the end of the seminar. So I'm about to stop the recording, and then we can open up for questions, and you can turn your cameras and microphones back on. The next seminar should be a doozy. It's called Ethics for Engineers, and we go into a whole range of issues and look at some case studies.